All right, well, why don't we get started? Looks like most people are on. I haven't seen the participants count go up. Oh, there we just went up two more. But why don't we go get started? I'm Roy Barnes. I'm going to be hosting this today. It's my pleasure to welcome you all here to our first virtual astrobiology seminar from the University of Washington. So bear with us. We might have some logistical issues, but I'm hoping that today will go off without a hitch. It's my pleasure to introduce Professor Jason Barnes, no relation, from the University of Idaho. He's going to be telling us about the Dragonfly mission. The way that I'm hoping that this will go today is once I'm done with the introduction, we're going to hopefully be able to mute all of your mics and block all your videos to keep the bandwidth high so that we can all hear Jason and hopefully see some of his videos. And so then once his presentation is over, we'll then open it up to questions. We're nearing 100 participants right now, so not really sure how the Q&A session is going to go. I'm going to try this time to just see how it goes with just people asking questions. But if you hear somebody speaking and you have a question, try and stop speaking, and then hopefully you'll have a chance to ask all your questions you want. Yes, and as Vicky's saying here, you can also write questions in the chat window as well. So hopefully this will go smoothly. With that, let me introduce our speaker, Jason Barnes, who hopefully you can all see. So as I mentioned, Jason is a professor at the University of Idaho. He began his career at Caltech, where he ended up working with somebody some of you might know, Victoria Meadows was one of his first research advisors. Then from there, he went to the University of Arizona's Planetary Science Department, working with Bob Brown. He then stayed for a couple more years at the U of A as a postdoc working with Cassini. From there, he went to NASA Ames to work on the Kepler mission before settling in Moscow to take his position at the University of Idaho. So with that, and I guess the last thing to say is, of course, he is the deputy principal investigator for NASA's Dragonfly mission, which is the topic of today's presentation. So with that, I'm going to try and pass it off to Jason and let him give his presentation. Please, sir, take it away.
Okay, thanks, Rory. Yeah, sorry you have a beautiful view of, the ceiling of my bedroom, but I guess that's how we're all living now, so welcome. Thanks for the introduction. Yeah, I worked for Vicky before all of you worked for Vicky. I was one of her very first students back in 1995. I did started my summer undergraduate work with her back when I was 18 years old. So she taught me everything I know, except the parts that you might hear that are wrong. So I'll take credit for those myself. But thanks for inviting me out for the talk. I really appreciate it. And I wish I could be there to actually visit you guys all in person. But maybe we'll get the chance to do that again someday in the future, because this is just how things are these days. As Roy mentioned, I'm the deputy principal investigator for the Dragonfly mission to Titan, and that's what I'm going to be talking about today. Dragonfly is a nuclear quadcopter lander going to an exotic moon of Saturn, which kind of sounds crazy when you put it like that, okay? And this is definitely a very aggressive mission concept. But by the end of today's talk, I hope to convince you that far from being crazy, this is actually the most rational and best thing that we can be doing with our planetary science program these days. So let me get started by talking some background about Titan and why we're going and the science we'll be doing, and then I'll talk about a little bit more about the mission, and I'm going to try to leave a lot of room for questions at the end. Okay, so I like to start thinking big picture. Okay, why are we going to Titan? Why is Titan worth sending this big $850 million mission? Well, when you really think about it, there's only 4 places in the solar system that have both a solid surface and an atmosphere like we do here on Earth, okay? I mean, there's plenty of places like Jupiter and Neptune and plenty of exoplanets that have atmosphere, and it's just atmosphere, it's just gas all the way down. There's no solid surface at all. And then there's plenty of places like the moon and Mercury and asteroids that have a solid surface, but no appreciable atmosphere that interacts with it. And then there are precious few places where you actually have both a substantial a solid surface and a substantial atmosphere that can interact with that surface. And those places are Venus, Earth, Mars, and Titan. Of these 3, Titan is in some ways the most Earth-like. In some ways, Mars is the most Earth-like. I think these are the two competitors for most Earth-like surface. Of course, Mars is closer to Earth in mass. It's 1/10 of an Earth mass, whereas Titan's more like 1/50th of an Earth mass. And Mars is mostly made of rock, whereas Titan is mostly made of water. And the temperature, of course, on Mars is much closer to the temperature of Earth than Titan is. Titan on the outer solar system orbiting Saturn has a surface temperature typically around 90 degrees Kelvin, or 90 kelvins, as measured by the Huygens probe. But when you start looking in other ways, Titan's similarities sort of come to the fore. For instance, if you look in terms of the surface pressure, Venus's atmosphere is 100 times thicker than Earth's. Mars is 100 times thinner. Titan's is just right. It's about 50% thicker than Earth's atmosphere in terms of the pressure. But because of the cold temperature, the density is about 4 times higher than Earth's. When you look at the composition of the atmosphere, of course, Mars and Venus have primarily carbon dioxide atmospheres, whereas Earth and Titan share a nitrogen atmosphere, which is particularly helpful if you're running, for instance, tests on potential spaceflight hardware. If you just use a nitrogen atmosphere, it's real easy to do that, to simulate that in Earth standard conditions. The other strong difference between them, I would say, is the gravity, right? On Earth, you get 10 meters per second squared of gravity. On Titan, it's more like 1.5. But that combination of a thick atmosphere and low gravity make Titan the easiest place to fly in the entire solar system. And therefore, if you're going to put a helicopter or an airplane anywhere in the solar system other than Earth, Titan really is the place that makes the most sense. Thinking of Titan in another context, as an ocean world, I said Titan is mostly made of water by volume. And that's true. And that puts it in the class of planets and moons that we now call ocean worlds, those that we know to have a significant amount of liquid water, most of them below their surfaces and not on their actual surface today. And this plot that I borrowed from University of Puerto Rico doesn't include Enceladus, which would be a very small object about this big on here, about 500 kilometers across, but it should probably be in this family portrait of ocean worlds as well. Of course, the Earth has an ocean covering its surface, but the actual volume of water that that ocean takes up is relatively small, right? It's a couple kilometers thick, and Earth is 6,000 kilometers in radius. So the amount of water on Earth is just a really thin veneer right on the very top. If you go to some of these icy moons in the outer solar system, like Europa, Ganymede, and Titan, they're structured such that their entire mantle and crust are basically made of water. And the very outer layer tends to be frozen. And that's of varying thickness. It's probably thinnest for Europa and pretty thick for Ganymede and Titan, maybe 100 kilometers, though we don't know exactly how thick. And below that is a liquid water layer. And we know this from Europa based on magnetic signatures of Galileo's flybys showing a conducting layer, as well as looking at just the surface geology and the fractures on Europa's surface, which seem to indicate that you have a water ice crust overlying a liquid water mantle. And so if you're just, thinking about where can life exist in the solar system? Well, you'd think that the conventional naive 3 requirements are that you have energy to be able to support biology, water, or perhaps another solvent, and we'll talk about that in a couple minutes. And you need carbon and other elements necessary to be able to build up complex molecules that can carry information and execute biological chemistry. So of these in the solar system, we've sort of been looking for water. Okay, that was the goal of the Mars exploration program, and although there's no liquid water on Mars today, there has been in the past based on the surface geomorphology, and there may be even today subsurface water like a groundwater layer, because we definitely see lots of water ice on Mars. But if you're looking for places, other places where there might be water and you might have life within water, perhaps these icy moons of the outer solar system that are made mostly of water and have very thick liquid water oceans are a good place to look. So that's one of the reasons we want to go to Titan. We know there's water, there's liquid water beneath the surface, and the surface is made itself of water ice. However, the real reason that Titan among these is the most compelling target, I think, is not the water, it's the carbon. We now understand that there's water in many of these icy moons in the outer solar system, and perhaps even around Ceres or Pluto, Triton, there might be many ocean worlds that have these thick liquid water layers underneath their icy crusts. What sets Titan apart is the carbon, okay? Titan's atmosphere is mostly nitrogen, but has a very small amount, around 5% on average, that is methane. And methane in Titan's upper atmosphere gets photolyzed by solar ultraviolet, ripped apart into smaller molecules that then recombine into larger and larger complex carbon chains and slowly rain out of the surface. So what you're seeing on the left here is a visible light image of Titan from the Cassini Imaging Science subsystem. Doesn't look like much, does it? When you look at Titan from the outside, all you see is this thick atmosphere that's composed of these carbon chains that have been photolyzed by solar ultraviolet. They put themselves together into little small solid aerosol particles that inhibit your ability to see through to the surface at visible wavelengths. And those little haze particles, what we call them, think of it like smog in Los Angeles, okay? I mean, smog back when cars were driving around Los Angeles and putting out smog. I hear it's real clear these days. But when you try to look through Titan's very thick atmosphere, there's enough of these haze particles that prevent you from ever being able to see down to the surface. But it is those very carbon molecules that are sort of an inhibition on our ability to be able to explore Titan that really make it exciting, particularly from an astrobiology perspective, okay? Because they provide the carbon from which you can potentially build up prebiotic and possibly biotic molecules to start the process of how we think may have formed life on Earth back 4 billion years ago. And so that's really why Titan, I think, is the most compelling target. It has interesting geology and interaction with the atmosphere, but it also has the 3 elements we think you need for life. There's plenty of sunlight at the surface to provide energy. We think there's liquid water beneath the surface and possibly transiently at the surface, and we'll talk about that in a bit. And there's more carbon and more carbon complexity on Titan than anywhere we know of in the universe other than Earth itself. The Cassini mission, which arrived at Titan in the Saturn orbit and executed 127 flybys of Titan between 2004 and 2017, was able to see through this haze. It was designed in some way, in part, to be able to penetrate this haze and see down to the surface so we could see what was going on. And I'm showing a video on the right here, this rotating Titan, showing what Titan looks like if you look at longer infrared wavelengths. So if you look out at 5 microns, which is 10 times longer than visible wavelengths, the size of the haze particles is about a micron. So you try to hit a haze particle with a half micron photon and it bounces back. You try to hit it with one that's 5 microns across and it just goes right through. So we can see through a lot of the haze. It becomes optically thin at longer wavelengths. When we look to the surface, this is what we see. Titan's surface is actually quite varied, okay? Initially, we had thought if you're producing these photochemical carbon products in the upper atmosphere, they get into the haze and they slowly fall out and they should just coat the surface and make it all uniform and look the same at the end. That is not what we see. Actually, Titan has a very interesting and active surface geology that's driven both by winds and by exciting fluvial processes as well, which we'll get to again in a second. Sorry, I got so many teasers. I don't normally do that. Okay, so what we want ultimately to be able to explore with Dragonfly is these prebiotic and potentially biotic chemical interactions that we think we will get when you get Titan's complex carbon molecules and you mix them inside liquid water. So how could you possibly get the carbon that's produced in the atmosphere mixing in with the liquid water, which is all 100 kilometers down? Well, we've come up with a couple different ways that we think that could happen. One is via what we call a cryovolcano. It's kind of a dumb name, but if a volcano on Earth is when you take, crustal material, melt it, and ooze it onto the surface. That crustal material is rock. If you melt it, that's lava. It comes onto the surface as lava and resolidifies. On Titan, however, the crust is made of ice and the mantle is made of liquid water. So if you take that liquid water from the mantle, ooze it onto the surface, it's effectively the same kind of a volcanic process that we see on Earth. And at left here is a 3D visualization of our best candidate cryovolcano at Titan. This one is called Sotrafacula, but this mountain here is called Doom Mons. We got the IAU to name mountains on Titan after mountains in Middle Earth, so that's fun. But the reason we think this could be a cryovolcanic edifice is this nice sharp peak. We have a very exaggerated here in the topography, a potential caldera or a pit on the side, and there's a bunch of flows that head off to the northeast, which is down in this image, that may represent what a cryolava or water flow could look like on Titan. But I mean, we don't really know for sure what it would look like because we haven't for sure identified it yet. We think this is our best candidate, but when we're sending a whole mission to Titan, we weren't really confident enough that this is really a cryovolcano to be able to target our mission, to be able to fly to it and see it. You can see it right here. There's a striking resemblance of what we see at Titan to this particular mountain caldera complex at Io. And so that's really just this broad scale topographical similarity that causes us to think that this could be a flow. But until we sort of get down there and see one, it's kind of hard to argue that for sure. But what would be exciting about a cryovolcanic flow is there are two potential things you could do with that. And that one is if you have flow on the surface and you get liquid water then interacting with the organics that have been deposited from the photochemical processes, you can mix those two and start to introduce oxygen into the molecules and allow them to interact as may have happened on the early Earth. So it's just seeing that interesting carbon chemistry when you get natural products and mix them with water could be interesting, but those flows might be pretty thin, and so they might not be liquid for very long. But if there were extant biological or pre-biological chemistry going on in the ocean itself, oozing that material on the surface allows you to directly sample it. One of the potential difficulties at Europa, of course, is if you want to sample the ocean, you might need to drill down 5 or 50 kilometers to be able to get down to it. It'd be much easier if there were some mechanism that brings ocean material up to the surface and deposits it there. And a cryovolcano could be one way to do that at Titan. However, we think a better option is to look at impact craters. So this is an impact crater called Selk that's about 80 kilometers across from rim to rim. And the advantage of an impact crater is that when you look at impact craters on Earth, Venus, Mars, the moon, when you slam something into a planet at 15 kilometers per second, 20 kilometers per second, a lot of that kinetic energy ends up going to melt the target rock. So if you melt some rock on Venus, it turns into lava, and we see lava basaltic flows coming out of craters on Venus and craters on the moon. But the target rock on Titan is water ice. So when you get an impact into Titan, you melt a substantial amount of the target water ice. We estimate that for this 80-kilometer crater, it should have produced a impact melt pool about 100 meters thick that may have been able to remain liquid for upwards of 10,000 years because of how long it takes for that conduction to cool that flow. That's what we think is particularly exciting, being able to mix organics and liquid water, leave it for 10,000 years. How far does prebiotic chemistry progress? What pathways does it take? Can we use this as a laboratory to be able to explore what we previously thought we were unable to explore, which is the origin, the chemical origin of life on early Earth? So this is one of our primary targets. Since you guys are an astrobiology audience, I will tell you the full story though, and that is that we don't necessarily assume that water needs to be the only possible solvent that life could operate in. There's also a chance for, life, Jim, but not as we know it, with a different solvent on Titan, because that methane in Titan's atmosphere sort of plays a very similar role that water plays in Earth's atmosphere, because it's near its triple point, okay? So methane on Titan has a local humidity that changes across the surface. As you take a parcel of air with methane vapor in it and convect it upward, it will cool off, and in doing so will form clouds. And these are infrared views of Titan, showing clouds in blue or white. The haze here kind of comes up pink, and the green is the surface in this color scheme. But these clouds appear on Titan. They seem to billow up to the tropopause, about 50 kilometers altitude, and come out. So these are effectively thunderstorms, what we would call on Earth thunderstorms, that we see within Titan's atmosphere. And those thunderstorms are made of liquid methane droplets. They form rainfall, and we've seen places on Titan's surface where it has rained. We see the surface darken and then relighten after a storm. We see other channels and other effects from this liquid methane as well. This is the only other place in the universe that we know of where it actually rains. That rain interacts with the surface and provides the primary mechanism for erosion, the same as we see on the Earth. And so that makes Titan exciting from a geological perspective. It's this rainfall-driven erosion that's the dominant surface process, but also because that liquid comes to the surface and erodes channels. These are views of fluvial river channels that were observed by the Huygens probe. The Cassini mission dropped a probe into Titan's atmosphere in 2005 that took images on the way down. And these are some 3D reconstructions of these black channels that look very similar to rain-driven channels on Earth. They're dendritic, they start small, they grow into larger and larger channels as you get moved downstream and downhill. And if you look at Titan's North Pole, so the North Pole of Titan is about right here, you see these dark splotches, which are lakes and seas of liquid methane, possibly mixed with ethane and other hydrocarbons, near Titan's North Pole. We actually didn't see these initially with Cassini, and the reason is that Titan takes, since it's orbiting Saturn, it takes 28 years to go around the sun, and it's tilted, has an axis tilt of about 26 degrees, not too different from Earth. But we arrived in northern winter, and so it was dark there. So like we just actually could not see these lakes and seas until the sun came up around 2008, 2010. And that illuminated the North Pole and allows us to see that there are these actual open bodies of liquid sitting on the surface at Titan. Once again, this is the only other place in the universe that we know of where there's active lakes just sitting out on the surface and in equilibrium with their environment. But these lakes bring up this additional possibility of another possible solvent, another liquid in which chemistry might be able to progress toward biology. So we, as the Dragonfly mission, we are actively looking for both the chemistry that would occur aqueously in water, where as might occur in an impact melt or in a cryovolcanic event, and also that might occur in these North Polar lakes and seas, and may leave its remnants, as particulates, as sediments near the shoreline. In fact, we don't think that the seas themselves are the best place to go to do this exploration. And one of them is that you can't get to the liquid water stuff there. And second of all is that, you know, imagine, okay, you're aliens from HD 209458B's outer planetary cousin, and they're arriving at, you're sending a probe into Earth, and you want to look for life. Should you really like land in the middle of the Pacific Ocean because that's the biggest expanse of water, and you think that's water is where life is going to be coming from? You might think so, but right, if you actually did that experiment on Earth, now the Pacific is probably going to be one of the places where there's the least amount of life anywhere on the surface, okay? What's a more interesting place maybe would be the shorelines, maybe lagoons behind the ocean, where you're depositing lots of gook, lots of algae and products of biology that are being deposited there. I really think that the shorelines material sediments are actually a much better place to look than inside the liquid bodies themselves for chemical evidence for biology or prebiotic processes. We happen to have giant mountains of these sediments on Titan in the form of its sand dunes. So this is a view from Cassini's radar instrument. And these linear features that you can see here are giant sand dunes that organize themselves near Titan's equator. The composition of these dunes, I call them sand because to those of you that are geologists know that sand is sediment with a particular particle size between 0.0625 and 2 millimeters as the modal particle size. So if you calculate what size particles should saltate around and form sand dunes on Titan, you get 200, 300 microns, very similar size to sand grains on the Earth. However, these particles are not made of silicon dioxide or basalt or any of the other kinds of dunes that we've seen elsewhere in the solar system. Their spectrum and their emissivity, their radar response properties are consistent with organics. So these sand dunes seem to be made of organic particles, 200 to 300 microns in size, and they organize themselves into giant 100-meter high sand dunes that are tens of kilometers to hundreds of kilometers long, separated, 3 or 4 kilometers between each peak. And these look very much like the kind of longitudinal sand dunes that we see on large deserts on the Earth. This is a picture of the Namib Sand Sea in Southwest Africa, which I was fortunate enough to visit. These crests just go as far as the eye can see into the distance. And there's another crest here 3 or 4 kilometers away. Okay, I admit, my background is in astronomy. I had to learn that in these sand dunes, they organize, this is just an amazing thing, that these quadrillions of tiny little sand particles organize themselves into particular mountains where there's sand, and then between them, there are interdunes where there isn't any sand. Okay, you climb down to this interdune, it's gravel, particulate gravel about this big. There's no sand there at all. So this is particularly exciting for us from an exploration perspective. Dragonfly's initial landing site will be within sand dunes. We think that will look very much like this, with the goal being we'll be able to measure the composition of organic sediment particles and the interdune areas, which we think should be made of water ice, and they should just be a couple kilometers away from one another. So really easily achievable from an exploration perspective. And then our long-term goal will be to slowly leapfrog our way over to the Selk impact crater, where we believe we'll be able to directly sample and measure the composition of previously liquid water within the impact melt sheet of that crater. Okay, so usually I don't talk about this part, but you guys are astrobiologists, so you get the full experience. Dragonfly actually has an explicit scientific goal. Our goal 5 is to search for chemical biosignatures within the surface of Titan, at the surface of Titan. And as far as I know, we are the first space mission to have an explicit goal to search for life, to search for chemical biosignatures since the Viking landers in the 1970s. We like to think we're taking a step back and taking a very different approach than the Viking landers. Of course, the Viking landers took Martian soil and they put it in a nutrient broth and they waited to see if something would grow in it. In retrospect, we really did not understand enough about Mars, its environment, and what we were looking for to be able to do that experiment in the 1970s, in my opinion, okay? Turns out we understand now that the perchlorates in the Martian soil are such that when you put them in water, they create an acid that if there was life on Mars and you put the soil and water in with it, it was definitely dead after that, okay? That would definitely have wiped it out. So we're taking a step back. Instead of looking for active biology, we're just looking for the chemical signatures of that biology, right? It's the difference between, okay, you're looking for your neighbor's dog. Sure, you could set up a webcam and like look for see if the dog ever comes out. We're taking an approach. We're stepping back. We're gonna go into your neighbor's yard, okay, and we're just gonna look for piles of dog poop. That's more like what we're looking at. Okay, sorry to describe it that way, but my kids like it when I talk about biological processes in that way. Okay, so what we're gonna do is we're gonna sample the surface, and one of the things we're looking for is what we call, what Chris McKay calls the Lego effect, all right? We're looking for, it turns out, when you take biology and you look at biological organic molecules, there are a particular suite of molecules that biology on Earth preferentially creates, and that abiotic chemistry should not produce particular molecules in abundance. One way to think of this is via amino acids, right? Your body, your DNA codes for 20 different amino acids, and those 20 are produced at a very high frequency by your cells, and your body creates all of its proteins starting from those products, those particular 20 amino acids. But there's hundreds or thousands of possible amino acids that you can make chemically. So why does biology only use 20? You probably know better than me, but I think of it sort of like when you go to the hardware store, okay? There's like 2x4s and 2x2s and 2x6s and 1x6s, but you can't buy any random size board at the hardware store. It's more efficient to make particular standard sizes that are very common. And then if you really need to modify that, you can buy one of those and modify it. And biology seems to use the same approach. It produces particularly useful molecules in high abundance, and then doesn't produce other neighboring, perhaps just as chemically favorable molecules, because it prefers to concentrate on a few building blocks and build the buildings from those and modify those as it needs, rather to have a system that codes for every single possible amino acid. So when we look at the composition of Titan's surface, one of the things we're looking for is, do we see sort of this blue plot here that looks like molecules that would be produced according to chemical kinetics alone? Or do we see particular types of molecules of particular mass, that are produced in very much larger abundances than you would expect via achemical processes? So the advantage of this is that it doesn't make any assumptions as to, for instance, is this occurring in water or is this occurring in methane, liquid methane or liquid hydrocarbon? We're going to have to use context to figure that out, right? If we're sampling organic sediments, maybe that's coming from the seas. If we're sampling a water ice bedrock layer, presumably that's from liquid water. But by taking this step back, we're hoping to avoid some of the pitfalls and the assumptions that you might make if you think you know what you're looking for, and instead to just sit back and look for the patterns that biology or biological chemistry might produce instead. The other thing we're looking for is the chirality of the molecules we find. So when you look at molecules on Earth, sugars that are used by biology all have a particular handedness, and proteins all have the opposite handedness. I'm embarrassed, I always forget which one's which. Can someone remind me, are sugars left-handed and proteins right-handed, or am I backwards? Okay. But this seems to be just a random event that happened early in the production of biology, that you have a particular one, must have gotten started earlier, and that it's easier to just keep producing that particular handedness as you move forward. So one of the things we're looking for is abiotic chemistry. We think should produce a racemized mixture, basically both at this and equal amounts. Okay, Vicky says right-handed sugars, so I was backwards. Thank you, I appreciate that. Right-handed sugars and left-handed amino acids. Whereas abiological chemistry should produce about even amounts. In fact, the greatest sort of ratio we've seen from abiotic chemistry is about a 60-40 ratio in the Murchison meteorite. So one of the things we'll be looking for is, do you see particular organic molecules that are produced with an excess of one-handedness over the other, or do you see more of an even mixture, whereas a particular excess of one-handedness, whichever it is, would be indicative of possible biological selection to create those. And then the last signature we're looking for would be one of disequilibrium chemistry. So if you have some sort of critters, presumably in this case you'd be looking for those with a hydrocarbon-based solvent on the surface of Titan. Presumably they're going to be respirating, they're going to be interacting with their environment, and they're going to be preferentially taking in some particular molecules to be able to generate energy. A good option for that is hydrogen. So as photochemistry rips up methane molecules in the upper atmosphere of Titan, it leaves, it rips the hydrogens off, and the carbons go off and mix with themselves. The hydrogens end up forming H2 that eventually escapes from Titan just via kinetic escape, reaching escape velocity at in the upper atmosphere. But before they do so, there's some concentration of hydrogen in the atmosphere, and it's about 1 part per thousand, as measured by Huygens. This is a plot here that I'm showing. I'm showing a plot in the planetary way. Okay, so up is up. This is altitude, and this is the concentration of hydrogen on the x-axis. And that hydrogen concentration seemed mostly stable, but the very last point, when you get down to the last couple kilometers, seemed to be a little bit lower. If there were biology that were hydrocarbon-based at the surface of Titan, seeing a deficit of hydrogen into the surface, as if there were a hydrogen sink there, may be an indicator that you had some sort of respiration going on. I'm not saying I think this is happening, but it's a fairly simple and straightforward experiment for us to do as we fly down to the surface and fly up and down, fly around, to be able to look at this hydrogen concentration and see if there are variations, gradients that might indicate that there might be something, particular hydrogen sinks in one location versus another. This is one of the things we'll be looking for. As you all well know, there's no silver bullet when it comes to looking for biology, okay? You can't just whip out your tricorder and say, sir, there's life signs here, okay? I hope someday we can do that, but we can't yet. So no single indicator is going to cause us to make a press release saying, oh my gosh, we've totally found life on Titan. This is going to be a long scientific process by which we put in multiple lines of evidence to try to see if we can't figure out what's going on. But we are making that ambitious step to try to look and to claim this to be one of the goals of the mission. So in order to do this search, this is what we came up with, a mobile lander, and we call it a relocatable lander, or a rotorcraft relocatable lander, because we spend almost all of our time on the ground, okay? We spend 1 hour flying each 2 Titan days. So once a month, we fly for 1 hour. If there weren't a quarantine going on, you would probably spend more time than that flying around to conferences on average in a year, okay? We spend most of our time on the ground, doing experiments on the ground, monitoring the conditions on the ground, both atmospheric, surficial, and we have a seismometer to be able to read what's going on under the ground. And we only fly relatively infrequently, but we came upon this solution because we needed mobility to be able to get to both the water ice and organic sediments. And wheels can be kind of problematic. We don't know if there's going to be trafficability. We don't know, certainly if you're landing in sand dunes, the Mars people will tell you driving on sand is probably one of the hardest things they have to accomplish. And so really Titan's environment allowed us to come to the solution of, instead of achieving mobility with wheels, like they do on Mars, we achieve it with rotors to be able to take off the whole lander and fly the whole lander around, land in a new location, and do a new set of experiments. We're aided in this by the fact that we actually know what the surface of Titan looks like, at least in one spot. The Huygens probe, though, was designed only to sample the atmosphere on the way down. It's so easy to land on Titan because of the low gravity and thick atmosphere. It just had a parachute and it was able to survive the landing anyway. And it took this picture right here. This is an actual picture taken from the surface of Titan. On the right is sort of an analogous picture, as you might imagine, from the moon. And the reason is the lander was kind of pretty close to the ground here. So these rocks here are about 10 centimeters across, about the size of your fist. This light color makes us think they might be liquid or they might be solid water cobbles, but we don't have that information because Huygens wasn't designed as a lander. It wasn't designed to sample the surface materials like we will be. But certainly the flat nature of this terrain here is encouraging that we should hopefully be able to find safe landing sites once we get there. Okay, so we have 4 primary science instruments. One is our camera suite. We have 2 cameras looking forward, 2 looking to the sides, looking at where we're going to do we call our workspace, where our sampling system is. 2 microscopic imagers that are really zoomed in, looking at the drill hole that we will produce. And then 2 cameras up here that are on our radio dish so that we can articulate them around and generate a panorama of the environment. Once we sample material, we put that through our Cadillac instrument, which is the mass spectrometer, which is going to be measuring the composition and the chirality of the materials that we ingest. So that's, I would say, our most important experiment. We also have a gamma ray neutron spectrometer to get the sort of the bulk composition of where we land, to figure out, have we landed on ice, have we landed on organics, to be able to measure the composition of, say, salts, sodium, potassium, chlorine that aren't maybe as well measured in a gas chromatograph mass spectrometer. And then we have our environmental monitoring systems that measure the temperature and the pressure, the relative humidity. That we have a seismometer that we will place on the surface to be able to measure the amount of tectonic activity and potentially also measure the depth of the crust and how far it is down to the ocean. So there's an old saying among planetary explorers that when you design this thing on a CAD, you think you know how it's going to be, and it's always bigger than you think. So I knew that, and so I was imagining it was going to be bigger than I thought. And Dragonfly is even bigger than that, okay? This is a picture of what we call the Iron Bird, which is a mock-up to be able to, in this case, we're placing sampling lines. We have 1 drill on each leg, and that drill is connected to a sampling system. Sampling on Titan is easier than anywhere else in the solar system. Those of you guys that accept Earth. Those of you guys that are familiar with this on OSIRIS-REx, for instance, or on Hayabusa 2, they have to somehow collect material in a near zero gravity, very low, and then vacuum environment. On Mars even, if you have gravity, but the Phoenix lander, for instance, scooped up soil and then it tried to dump it into the thing, and it turned out it was much more cohesive than they expected. On Titan, we sample dirt the same way you do in your carpet. We have a vacuum cleaner. The local ambient pressure allows us to just use that to be able to ingest material. You could probably have a vacuum cleaner on Venus if you wanted to sample that way, but it's kind of like a flamethrower pointed inward on Venus given the temperature, right? So really this is the best way to sample, and where we ingest the material from the surface with these blowers, suck it into the carousel, do a sampling and blow it out. But this is the full scale thing. It's like 2 or 3 meters high. It's like 3.5 meters long. This is big. There's enough room you could lay in the interior. I don't recommend it because it's an 8.5-year journey and we didn't bring a life support system. But in principle, it's big enough you could fit in there. The whole thing masses about 1/2 ton. It is big. This is a big quad. So when you think quadcopter, don't think that thing you got your 8-year-old niece from Radio Shack. Think lander, rover that uses rotors to be able to locomote. I'm going to skip that one, even though it's fun. So how are we going to get there? We're going to launch in 2026 now, and we have we're on the cheap. We're getting there on the cheap, so it's going to take 8.5 years for us to get there. So I want everybody to, you know, eat their Wheaties, eat your vegetables. I want you to be able to make it. I want you to survive till we get there in 2034. Exploration of the outer solar system is a process for the patient, and it will take 8.5 years after launch before we arrive at Titan. But when we do, we think that it's going to look something like this. Hopefully, there's no audio on this, so I think you're safe. Hopefully, you guys can see it. This is a simulation of what it's going to look like when we arrive in 2034. We got a heat shield that's going to help us slow down from 7 kilometers per second to supersonic speeds when we'll deploy a supersonic chute to be able to get us through the sonic regime. After that, we got this low gravity and thick atmosphere. We're actually going pretty slowly. By the time we get to the lower atmosphere here, we're only going 3.5 meters per second. We drop the heat shield, and this is the rotorcraft all bundled up inside, using all the space we possibly can. We can deploy the legs, and then we let go from the back, process we call initial deployment and initial flight. And then we're going to fly around to find our safe landing site. We do have good orbital imagery from Cassini, but honestly, it's about 0.5 kilometer resolution. We need to find, is there a rock that's 1 meter across that could tip us over? So we have various systems to be able to identify that autonomously. We can fly for half an hour to be able to find that site. So there's no rush. We can look around until we find a safe landing site where we'll put down. And after that, we'll spend the next 3 years sampling various sites, flying between places. And what I'm really excited about is our ability to really sort of track down science, right? You land in one spot, you make a bunch of measurements. We don't want to say, oh, the composition of Titan is X. We want to say, oh, that's interesting. Where did this rock come from? Let's fly over there. Let's find the source. Let's figure out what's happening with Titan, and to be able to fly around, get to the optimal areas to do our optimal science. And we have both the capability and the means to be able to track down our scientific targets like that and explore over time until we can hopefully get to understand Titan in the way that we've been able to understand Mars with rovers over the last 20 years. Thanks. Do you have questions? Rory, yeah.
I'm back, yes. Thank you very much, Jason. I hope everyone is applauding him in your bedroom. So with that, I want to turn to, oh good, Vicky is doing it at least. With that, we're going to turn to a question. So I've asked in the chat room to please type them in. I think I'm going to follow the advice that was earlier in the chat room, just because there are so many of us that I'd like you to type them in, and then I will ask them for you. We have plenty of time for that, so we're going to go ahead and get started. So let's see, the first question was from Paul Unwin, who in the middle of your talk asked what would be a better name for cryovolcanoes than cryovolcano?
Oh, well, if you want to get scientists, especially astronomers, fighting, you start fighting about nomenclature, right? Get us starting about planets versus dwarf planets, or planets versus brown dwarfs. So I'm not going to go there. But if you can come up with a better one, I'm open.
All right, thanks. And then Paul also asked, is there lightning on Titan?
Oh yeah, great question. Well, I said I didn't mention that. I sometimes do. So we had thunderstorms, right? I put thunderstorm in quotes because evidently there isn't. Cassini, we listened very carefully for the radio bursts that would come with lightning. And we hear that from Saturn. Saturn is producing radio bursts associated with lightning. And additionally, we looked for lightning, we looked for flashes. And once again, on the dark side of Saturn, we can see flashes coming from lightning within the water clouds on Saturn. But we don't see them on Titan. So evidently there's no lightning, and we think that probably has to do with there not being a good mechanism for charge separation on Titan, because methane is a nonpolar molecule. So it has something to do with water itself. The water molecule allows you to be able to generate positive and negative regions of clouds that drive lightning, maybe, because we just haven't seen it there.
Great. All right, the next question is from Alan Caswell, who asks, how do winds on Titan impact flying ability?
Yeah, there are winds on Titan. We have measured them from Huygens, but the values were pretty low, you know, in the tens of centimeter per second. We think that there must be times when the winds get above about a meter per second because we've seen dust storms, and we think that sand at the surface saltates around, and that requires winds around a meter per second. We've also seen some waves on the seas that require, you know, require winds to be around 1 meter per second. So we think at the most energetic, that's kind of what we expect for the winds. We can fly at about 10 meters per second, so we can easily compensate for that. And because we only fly once every 2 months or so, we have an autonomous system that, you know, before we take off, we're monitoring the winds. The vehicle is on its own, and if it detects that the temperature is dropping and the winds are picking up, it will abort the takeoff and it won't fly. So we are quite confident that we can handle the winds that we expect to find. But even then, you know, there's no reason for us to fly in adverse conditions. And so if we detect anything that we think might in any way be a danger, we just wave off the flight and we fly on a different day.
Great, thanks. All right, next up is from Veronica Mirzajewski. Hopefully that's pretty close to your name. Sorry about that. Who thanks you for your talk, and then was curious if the Mars helicopter informed the design of Dragonfly in any way.
Actually, no. We developed this independently and sort of presumably in parallel. That they hadn't announced anything yet. To be honest, flying on Mars is like really hard. Okay, I mean the gravity there is 2 to 3 times what it is on Titan. The air is 200 to 400 times less dense. That's a real challenge, and that rover is sort of, you know, relatively small. It has actually rotors that are as big as ours across, about 1 meter in radius, yet the whole thing masses about 1 kilogram. So I will leave it to the Mars helicopter people to talk about their vehicle, but it's a very different scale and a very different kind of operation than we will be doing on Titan. On Titan, it's like a half-ton, fully instrumented scientific vehicle. More like if you took the Mars rovers and turned the whole thing into a helicopter than the Mars helicopter itself. But we wish the Mars helicopter all the you know, the best of luck in the world, because it's better for everybody if that works. We're really pulling for them.
All right. Next up is from Rudy, who says thanks, and then asks, how do you drill on Titan? If the stuff on the surface is hydrocarbon material, do you have to use a different kind of drill oil?
Okay, so we are definitely concerned about the materials. The kind of hydrocarbons and oily kind of stuff that you get on Earth, once you cool it to 90 Kelvin, is pretty brittle, so it's pretty solid. But we're still worried about that. We've done a lot of testing, particularly in phase A, of drilling into analog materials that are waxy or oily, and that's informed how we design the drill itself. Drill's has about a 10 centimeter depth that it can get to. And it's a hammer drill. I don't know if you guys have ever used a hammerhead drill to drill into concrete or whatever, but it's essentially percussing as it goes to try to get through the material. The hardness of the material is low enough we should easily get through it. The bigger concern may be if we suck that material up, does it gum up you know, our works? We have 2 separate sampling systems to provide some redundancy, and we do a lot of before we turn on the vacuum cleaner to suck in the material, we do a lot of visual inspections and you know, looking at how the tailings pile looks. Does it look like it's got like specular reflections as if it were partially liquid? So we have a lot of steps with the science team in the loop that we evaluate what that stuff looks like before we ingest it to make sure that we don't gum up the works. But we're definitely thinking about a very wide variety of materials and potential properties for the stuff that we plan on sucking up.
Great, thanks. All right, next up is Andrew Rushby, who asks, what considerations do you have to give to planetary protection for Titan? And how might protocols compare to Mars, for example?
Okay, so we have not yet gotten an evaluation from the Planetary Protection Officer, so we don't have anything definitive. In the past, the concern for Titan missions is don't forward contaminate the subsurface ocean. So ensure that there's no chance that we're going to fall into a rift that would allow the spacecraft that might have terrestrial cells still on it to get down into the subsurface ocean. So that's really the concern. There's no concern that water-based life is going to live in liquid hydrogen or anything like that. And even our RTG, which could create a local surface melt pool, as long as that pool doesn't melt its way all the way down, and our calculations show that it should not. It doesn't seem to be a concern and hasn't been a concern in the past, but we look forward to interacting constructively with the Planetary Protection Officer moving forward.
All right, next is another question from Paul Unwin, who asks, have experiments on Earth indicated that methane biology what methane biology might look like and how it might behave in Titanian conditions? People have done experiments. The solubility of carbon molecules is pretty low, and the kinetics of reactions are much lower, so it's definitely going to look very different than biological molecules do on Earth, right, that are evolved to have maximum activity at around 300 Kelvin. But I don't think there's any reason a priori to think that it wouldn't be possible to construct molecules that might perform similar functions in much lower temperature conditions. For instance, we know that you can produce biological molecules that do the same thing in higher temperature conditions. If you look at the deep sea vents, for instance, they all have taquinases that will reproduce DNA, and they all operate at 430 Kelvin because the local conditions there are above the boiling point that are kept from boiling by the overpressure. And those particular bugs that live there have evolved these different enzymes that operate at very different temperatures and pressure conditions than the ones do here. So although we think it should be possible, it may be possible. I'm not saying it should. It's a possibility, and I think there's a lot more both laboratory and theoretical work that need to be done, as well as this active experiment of going out and looking to see what actually gets produced in those lakes and what it might be doing chemically. Okay. The next question is from Mike Wong, who says, what kind of AI technology still needs to be developed for autonomous flight on Titan? And is there a back and forth with the Perseverance team to learn and share technology being developed for the drone associated with that mission?
Okay, so yeah, we do have, this is one of our challenges, is to be able to do autonomous flight and landing. We have a lot of tools to help us do that, radar, imaging, an active LiDAR system. It really helps at Titan that we're not in a rush, okay? On Mars, you've seen the videos of the 7 minutes of terror as the thing flies screaming in. It's going to run out of fuel in 30 seconds unless it lands right there. We're much more relaxed. Okay, we got half an hour. We can look around and take our time to find actively find a safe spot. We don't need a spot that's 100 kilometers long that's all safe. What Mars does, right, is they look with HiRISE, and that has pixels this big, and they look to see if there are rocks this big, and if they don't see any, then it's safe. We just need a 10 by 10 meter-ish, area with its flat and free of rocks and topographic obstacles, and so we've got plenty of time to be able to find that. I think our bigger challenge is something, or not a bigger challenge, but something that's more unique, more unusual, is flying. So we have this strategy. The very first landing, it's got to be entirely autonomous, okay? It's going to have to do it all on its own. Subsequent landings, we don't want to require that in the future. And so what we've evolved is this leapfrog strategy where we fly out 2/3 of our range, take pictures, and then fly back 1/3 of our range. And we keep flying back out 2/3, back 1/3, in order to be able to always land at sites that have been pre-scouted by both the engineers and to look for a safe spot, and the scientists to look for the most interesting spot. And so because we're going to use that, the ability to be able to find that spot again and to do active visual navigation is something that we're doing that the Mars rovers don't have to do, at least not from above. And so that's really our challenge, and we haven't had a lot of interaction with the Perseverance team with respect to that particular effect.
All right, great. Now, before I go on to the next question, I just want to let everyone know that we've reached 4 o'clock here on the West Coast, so if you did have another meeting to go to, you can feel free to drop out, but I think Jason's going to stick around and keep answering questions. Is that right?
Yeah, good for me.
All right, great. So, all right, so we'll just move on. So the next question is from Diana, who asks, in the plot where you showed hydrogen abundance as a function of altitude, what's driving the large uncertainty at approximately 45 kilometers?
Right, so can I get back to that? Wrong way. The Huygens probe actually, when it was in the upper atmosphere, it had a big parachute to ensure that it didn't move too quickly. That parachute, in fact, is so big, and it slowed it down so much that we would have run out of battery and Cassini would have flown by the time we got to the surface. So we had to ditch the big parachute and go to a smaller parachute to get down faster. And so we're actually moving a little faster at this part of the atmosphere. We didn't spend as long there, so we didn't have as many opportunities to sample and as many points to add together, and that's what's driving this larger uncertainty.
Great, thanks. So the next one is from Josh Pepper, who asks, how much of the sampling, observing, and travel decisions will be pre-programmed versus autonomous?
So we do have, because we have this sort of, we only fly every 2 months, we do have the ground is going to be in the loop for a lot of events. During flight, of course, there's an 1.5 hour light travel time out to Saturn, and we can fly for about an hour, so that's all autonomous, okay? There's going to be no joysticking involved. But once we land, we have a couple of pre-programmed sequences, like take a panorama, upload the panorama, take pictures of what we've landed on and what the drills might be encountering, do the gamma ray neutron spectrometer experiment to see if we've landed on ice or organics. And all these effects, the imagery, the atmospheric and surface conditions, the composition will inform whether we drill with the left drill or the right drill, what kind of experiments we want to do, what kind of, whether we want to run it through the gas chromatograph, whether we want to run laser desorption mode experiments to be able to really narrow down on not just a molecular mass, but a potential structure. And so we have a lot of options and a lot of time. Essentially, you know, once per day, the science team will be making decisions and uploading them. Once per day during, once per Earth day during the Titan day. Of course, there's 8 days of Titan night as the moon rotates. And so during that time, won't be much for us to do. We'll be able to, go back to our families, get some sleep, think about what we're going to do when the sun comes up, and the vehicle will be able to recharge its batteries. We run off a radioisotope thermoelectric generator, but it doesn't produce enough power for us to fly. We have a bunch of batteries. Those batteries are trickle charged by the RTG, and we fly on battery power. And so we really do need to, like your phone, right? When you plug in at night and plug it, and it's got enough power to run for the day, we essentially charge our battery overnight from the RTG and run off the battery during the day.
Great, thanks. All right, next up is from, I believe, Roy Black, who asks, do we know anything in detail about the organics on the surface? For example, are there amino acids?
That's what we're trying to find out. The Huygens probe, because it wasn't designed to get to the surface or sample the surface, and we didn't even know whether to ask that question, to be honest, when it was designed. It had a mass spectrometer that just had an air inlet, so it was able to sample the air on the way down. After it landed, it did detect some methane that was evaporated out of the surface, probably by the hot probe after it landed. But no one has done those measurements yet. All we know is that we've seen water ice spectroscopically. There's been some maybe spectroscopic evidence for ethane and possibly benzene. And that's the limit of our knowledge of the surface chemistry. There are measurements of very extraordinarily complex molecules actually from the upper atmosphere. Cassini flew through down at up at about 1,000-kilometer altitude, and Cassini was designed to be able to measure molecules up to a mass of 100 AMU, and it saw things upwards, and so it saw plenty of stuff up to 100. And in fact, there's even evidence on the dust analyzer of molecules of thousands of AMU in size up in the upper atmosphere. So there's every reason to suspect that the chemistry is going to be very complex and interesting once we get to the surface, but this will be the first measurement of what we find. And amino acids were actually one of our driving cases. The upper mass requirement for the mass spectrometer is that they'll be able to measure the mass of tryptophan at 550 or so.
Thank you. All right, next up is a question from Chris, who asks, how will Dragonfly avoid landing on semi-stable land, e.g. an equivalent of quicksand on Earth?
You can always devise some pathological system that we wouldn't be able to survive on. And there's no, system that you can build for finite mass and cost that could be able to survive anything. At the same time, the Huygens probe landed, and it was fine for about an hour at least, as long as we were able to continue to receive data from it. And when you just know about the strength of particular surfaces, this has been a concern right at the moon, right? For the moon landings, that you'd land and the material would be unstable and would suck you up. We think that we have a very, wide, very large area for our landing fleet. The evidence we've seen of the geology looks like things are fairly strong. Even in the sand dunes, you can land on a sand dune. You can walk around on a sand dune. It's not going to eat you up. And we also have the rotors have a much higher power capability than we're going to use in stable flight. If we really crank those things up, we can get a thrust to weight ratio well above 2. And so we can if we really get stuck in something, we can just pull ourselves out of it, as long as we don't go, lower than the belly of the vehicle. But we don't really expect that to happen. But there's a lot of capability that we can have to get ourselves out of trouble should we get into it.
Great, thanks. All right, next up is Don Brownlee, who asks, could you tell if Titan previously had liquid nitrogen oceans? They could have been tens of kilometers deep.
I think one of the most exciting things I want to do is to be able to, if you've ever been hiking in the Grand Canyon, you just see layers through geologic history, and you can just read off what's happened in the history of Arizona there. I would really love to be able to do this on Titan. But Titan is going to have to cooperate. For instance, in the walls of Selk Crater, I'm hoping to be able to see these kind of layers. And there very well may be chemical or microscopic topography or microscopic texture signatures of what you might expect from a liquid nitrogen ocean. I think you'd want to think about what kind of sedimentary layers that kind of condition would leave behind. But I suspect they might be very different than the ones we see today. There might be very low in organics, and maybe a lot more water ice that gets reworked and deposited. So I think we'd have to think about a little bit about what kind of a stratigraphic signature that kind of a condition might leave behind. But I think that's one of the most exciting things we might be able to do, which is be able to look back at the stratigraphic history of Titan and read back its geologic history.
All right, thanks. Next up, Ethan asks, what is the expected lifetime of the probe?
Well, our nominal mission is 2 years, 8 months. So that's how long we think we need to be able to land in the dunes, do our science there, fly to the crater, and do our science there with plenty of margin. But there's no real upper limit. We have very few consumables on board. The number of sampling cups in this carousel is one of the consumables. But at the same time, we can reuse them after we've used them before. They'll just be a little dirty. Eventually, we will run out of the RTG will run down, but the Voyagers have been flying for as long as I've been alive, 40 years, and they're still going. So it's actually the thermal output of the RTG due to radioactive decay that might be our ultimate lifetime limiting factor, but that could be decades.
All right, thanks. So next was a question from Emma Turtleboom, who I think she asked a question similar to Mike Wong, so I'm going to move on to Evan Sneed, who asks, with Huygens observations that there is likely less hydrogen near the surface of the moon, you mentioned the possibility that this could be a biosignature. Do you know of any abiotic geologic processes that could mimic this observation?
Sure. There's no reason. There could very well be geologic sinks for hydrogen in the surface. So this is going to be one of those things we're going to have to not just be able to make one measurement and say, oh, there's the answer, but rather to be able to look and see if that gradient toward the surface varies geographically. Does it vary seasonally? Does it vary diurnally? So we're really going to be looking at, very broadly, looking at if we were to see a signature, where it might be causing and what conditions it has. Could be there's like the dunes themselves tend to absorb hydrogen somehow or something, right? In which case you might see a spatial variation across the latitudinal or longitudinal variation across the surface. So we're going to be considering that very broadly, and do not expect us to, make one measurement and declare, that we've found life in the universe. That's not the way we plan to operate. We really want to make sure that we're doing a very broad-based fundamental science investigation, and that's really what we're focused on.
Thanks. All right, next up is Paige Northway, who asks, how are you keeping the instruments warm enough without affecting the surrounding area and thus the measurements?
Yeah, no, this is a real problem that we have to consider. We got a lot of insulation is one answer. We got like a lot of insulation across the whole vehicle. We're kept warm by the RTG. We actually have a thermal loop that goes through the RTG and takes heat from the RTG and uses it to keep the body of the vehicle at about freezing, about 270 Kelvin maybe on average, though that could vary with as we progress with the design. We're very concerned about potential effects on the environment, primarily due effects on the winds and the temperature measurement, right? You're trying to measure the winds, and you're basically creating a huge plume from your hot RTG. So because of that, we have wind speed and direction measurements on each of our stalks that host the rotors, and the final wind speed and direction and temperature measurements are going to not be just the raw values, but rather modeled values, given what they should what we'd expect them to look like, given the winds from a given direction, given the perturbation of the RTG. We're hoping that presumably one of them is always going to be upwind and should get a good temperature measurement that'll help us to guide this. But this is going to be a complex process that's going to be it's unfortunately not going to be as simple as just taking the number off the spacecraft and calling that good. We're going to have to model out what that measurement plus the perturbation mean for the actual conditions in the ambient environment.
Next, Arshuri asks, is the crust of Titan completely water ice, and are there tectonic plates causing earthquakes which interact with each other? Also, will activity like methane rivers, deltas, other water bodies happen through the fluvial channels being created?
So there are no plates. There's no plate tectonics. There's only plates on Earth, interestingly. We don't see plate tectonics on Venus. Maybe there's some evidence, maybe in ancient Mars. And we don't see any evidence of plate tectonism on Titan either. However, there are still earthquakes, for instance, on the Moon, and on Mars without plate tectonics. Earthquakes do not require plate tectonics themselves. You can still get faults, and you can still get faulting and crustal motion without that particular plate tectonic process. So we think that tidal forces in particular may be a source of seismic energy. Titan's orbit is a little bit eccentric, so when it gets closer to Saturn, it gets pulled a little bit more egg-shaped, and when it moves away, it gets more spherical, and so this happens once every 2 weeks, and this process may excite earthquake systems. We do, interestingly, see mountain ranges on Titan, which are really unusual in a planetary context and imply that there is some tectonism ongoing at some level. But as far as what the nature would be, we've only ever blown a seismometer to Mars and the Moon, and the ones on Mars have detected only a handful of quakes so far. So it'd be really exciting to just see what mechanisms exist to excite seismic energy on icy moons, and what do they tell us about the processes that are ongoing within the crust and possibly beneath it, and that's really our broad goal for the seismometer.
Right, and then the second part of the question was, will activity in methane rivers and deltas and other water bodies happen through the fluvial channels being created?
Yes, we in fact have seen deltas and river valleys formed from orbit. So we fully expect that to occur on Titan. And what's exciting with Dragonfly is we'll be able to see that process, from the ground, right? We've seen it at half a kilometer per pixel level, which, okay, what can you really tell from that? We'll be able to get down there and actually sample the various sediments and the different cobbles that get brought along by the streams in situ, and we're really excited to do that.
All right, and next, Patrick Gray says, I may have missed this, but what is the flight time and endurance per flight?
So the flight time depends on a lot of variables that we're still developing. We're still finalizing the very last bit of the design, And it actually is very sensitive to, for instance, drag. Okay, so we're going to be flying at 10 meters per second, but how far we can go involves how much energy we have to, how much power we have to put into pushing the air out of the way. It's really interesting because normal spacecraft, you don't have to worry about drag, okay, right? You know, like you look at the moon lander, it's got all that angular stuff going on. But we actually had to put these little fairings, these little nose cones over the drills because it turned out those were a huge source of drag. So this is ongoing. We should be able to fly for half an hour, you know, somewhere in the vicinity of a couple tens of kilometers, maybe total range, maybe a little less than that. But that's something that's going to really very sensitively depend on the details of what the mass ends up being. But roughly, we'll fly for an hour, fly several tens of kilometers.
Great. Next up, Sea Battles said, first, thanks you for a very informative and wide-ranging talk. And then asks, could you describe the data links that get the data you collect back to Earth? Bandwidth and transit time, for example? Could you also describe the
Sure, it's about an hour and a half light travel time. This is the dish. It's about 1.5 meters in size, and it's a flat phased array that we keep on our back like a turtle, okay? Because we don't want it to cause a lot of drag while we're flying. So when we're up, we fold that thing back. And then when we land, we bring it up, and we have a direct-to-Earth transmission, so we don't have a relay or an orbiter or anything. And because of that, it's the data link is pretty low bandwidth. We can get maybe 1 gigabyte a year at the minimum. I think we'll be able to do better than that in the end. So think of 2 CDs of data per year, roughly, is sort of the minimum. For reference, Huygens uplinked about 20 to 30 megabytes. This is about 20, 30, or 30 times the Huygens bandwidth every Earth year, and that's just a minimum, right? We think if we get more dish time than we expect, or larger dishes than we expect, we should be able to do better than that. But that's sort of a rough order of magnitude.
And do these bandwidth and transit time issues affect the amount of required autonomy with the mission?
Well, certainly the thing has to fly on its own, so that definitely affects it. But we are really a bandwidth limited mission, right? Basically, the amount of science we can do is limited more by the bandwidth than anything else. For instance, we don't really necessarily plan to send movies of the flight or a lot of aerial imagery because we just don't have the bandwidth for it. And as that might improve with larger dishes or arrays of dishes back here on Earth, we'll be able to do proportionally better in terms of the amount of data that we send home.
All right, and Akalesh Varanasi asks, how many people will be involved in the piloting process? What sort of teams take part in the decision making?
Yeah, we have this planned out exactly how we're going to decide where we go and when we're going to go and what the conditions are. The science team is intimately involved, okay? We want to land in a site that is going to allow us to execute our scientific program and answer our science questions. And so we will be one of the prime effectors of where we're going to land, and the engineers will also be involved. We want to find a place that's safe. But basically, we have some pretty broad requirements that we don't have too much tilt and we don't have any rocks of a given size. And as long as we have that, the scientists will be able to make the determination as to where the most interesting place might be to land. And given our onboard autonomous systems, we think we can be able, since we'll have flown over and taken pictures, we'll be able to recognize that spot and put down within a couple meters of where we had planned. But that's part of what we're going to be doing for that 1 month while we're on the ground is taking images, uplinking the scouting images of the future site, and having a team making that decision as to where we're going to go next, so that by the time comes that we're ready to take off and execute that flight, we got that all planned out and we know what we're doing.
Great, thanks. All right, next, Brett C. Mommer asks, will there be attempts after the initial landing to fly back up into the atmosphere again to resample?
So we do have a plan to sample the very lower atmosphere. We call these atmospheric profiles, where we kind of spiral up several kilometers and then we spiral back down to be able to measure the atmospheric profile. And we do have an expectation that we plan to do that a handful of times, a couple times over the course of the mission at different times of day to be able to look at how that profile varies as a function of the solar position and how long you've had to heat the surface and that sort of thing. But we can only get up several kilometers. The height of the troposphere is like 50 kilometers. We're not going to get that high. We're going to get like 1/10 of that, maybe somewhere of that order.
All right, we've reached the last question. So
Okay.
David Goldstein asks, many of the planets and satellites we know of have plumes, geysers, volcanoes, and other things. Does the mission have the ability to explore an active plume, since it would be a key indicator of subsurface activity?
Well, we have to find it first, and I think that's going to be harder on Titan because of the atmosphere, right? The atmosphere is going to keep that plume contained in a way that plumes on Enceladus or Europa just expand out, or even on Triton can expand out and take up a bunch of space and become very obvious to be able to detect. So if we were able to see something occurring, either seismically or with the cameras, or even with the atmospheric monitoring instruments, we definitely have the capability to be able to go investigate, to go fly over there and see what's going on. And I think that's one of the things that excites me most about the mission, is not just what we plan to do, but what we're going to find and be able to follow up on that we didn't expect to see. And I think we really have a vehicle that's capable enough to be able to find out, to both do what we expect, but also to follow up on those unexpected discoveries and make really new and interesting scientific discoveries that we haven't anticipated.
All right, well, like I said, that was the last one. So thank you so much, Jason, for the great talk and for answering all these questions over the subsequent half an hour.
Yeah,
so,
thanks everyone for coming. I was really impressed with the attendance. Hopefully you had a good, a relatively good day on Zoom.
I think so. I think it went pretty well. So yeah, I do want to thank everybody who did join. We reached 115 participants. So we reached a lot of people. So I really appreciate you taking the time, Jason, to inform the whole world about the Dragonfly mission.
Yeah, we're really pleased by the amount of interest by both the scientific community and the public for the mission, and we really appreciate your support. We hope to bring you some amazing discoveries in 2034.
Yes, hopefully we'll be out of quarantine by then.
Yeah, that's right. All right, all right. Well,
all right. Well, thanks again, Jason, and goodbye to all of you, and hopefully we'll see you next week for the next meeting, for the next seminar.